Okay, since we're live, let's just yeah, let's wait a bit more and then let's let me draw here. Okay. Can you just confirm me that the audio is fine? I hope the audio is fine. Zero out of zero dropped frames. Okay. 0%, I mean, dropped frames. I actually have no idea. I want to share the link on a story, but I have no idea how to do it. Yeah, I'll start, but I just want to just share it on the story and then we'll begin. Okay, I think I shared it. Now what I will do is I will put some music on. I will listen to some music. You do that too. I really recommend just listening to something like Stevie Wonder, I don't know, Jacob Collier, some jazz, some funk, some blues maybe. I will do that, and yeah, we'll talk about what we're going to do on this stream. It's going to be more of a chill out stream, going to research some topics, learn about some new things, you know. There's always this, you have to sit down and chill, you know. Just just chill out with some good music, with some good people in the chat. So yeah, I hope I have enough battery to last for the whole stream. And yeah, we have really fun topics. Actually, the topics are on the left there. I already written some topics. We are going to learn about a lot of things which I don't know really, but yeah, but always nice. It's nice to learn new things. Just I will hate the commercials, the ads on YouTube. Okay, I think we can kind of start the stream. I will add some later on. If you want to skip on the stream, I can add some chapters there. Feel free to use the chat as much as you like, and just not spam. Please don't spam. Yeah. So the first thing on our list is actually Gaussian elimination, which we're very familiar with. It is used to solve systems of linear equations with n equations and n variables, or sometimes they vary. Let's say n equations and m variables. But if you want to solve the system, and there has to be like there has to be an actual solution to the system, right, of linear equations. In high school, you learn about the system of linear. You learn about the system of linear equations with two unknowns and two equations, and when you solve that, then you learn for three unknowns and three equations. But of course, linear algebra allows you to solve this system for n equations and n variables. But it's not that straightforward to actually implement. Why? Because I want to compare it. Because of the precision errors that may occur. Some snippets, even though they use full pivoting or something like that, but they have precision errors and can, even for 50 equations and 50 unknowns, have problem with solving the systems. So I want first to okay, they changed this. CP algorithms wasn't like that. I know, like, they have some new. Yeah, that's much better. They have some new theme there. Okay, so yeah, searching for pivoting element. Yeah, I have seen this snippet here. And interestingly enough, now we should estimate the complexity. The complexity is already very well known. They use bit sets here. Yes, this is the idea here. Therefore, the resulting Gauss-Jordan solution must sometimes be improved by applying a simple numerical method, for example, method of simple iteration. Now I know this, like the Jacob iteration for like, but this is finding the inverse. This is solution turns it two steps for first Gauss-Jordan and then numerical method taking the initial to the. I'm interested in like what kind of problems do you have for Kirchhoff's law. Well, Kirchhoff's law, I'm interested in problems like this and see well, and I see that goes up to 20, the number of resistors. This is pretty cool. I like this kind of problems. Let's see. So was your dad, as you know, is good in math? Was you asked his father to help him solve a simple problem to find out the resistance of the resistor system. Dad answered him, here's something to think about. You have to enumerate the conductor's nodes to write the Ohms Law for each conductor. Then remember the sum of currents at each node of the nodes except the first and the last equals to 0. You may assume potential in the first node equal to 1 and the last node equal to 0 due to the flow. So there has to be, actually this is done to have a flow. Then you get a simple system of linear equation. Hence you find the potentials in the intermediate nodes and the currents between all the nodes. I see how you get a system. I mean, you get a system, but it's left only to divide the voltage by the total current from the first node. Right, but the voltage. Thus is not good in math, so that was to write a system of equations himself and to solve it. Thus he looks at the end of the book of problems. There's another answer that tried to solve the problem again and got another wrong answer. That resolves the problem for the third time. That got tried to solve the problem and he decided, okay, a number of nodes in the circuit, number of resistors. So probably a resistor consists of 3 integers A, B, and R. The description is the resistance connecting A and B nodes. There may be many resistors between two nodes. Exactly. And nodes 1 and N rounded within 2 digits of Hey, isn't this possible just to greedily do? Just to you just have to output the total resistance, which means that we have to if there is in series, if they're in parallel, it's 1 over that. Right. So you could solve it for like a smaller, like from between two nodes, and then what do you mean, Vincenzo? For optimization purposes? Well, I don't understand why you can't solve this like on any other old way. Just solve it for like smaller, and then combine the answer and solve for bigger. So if you have like a network, I will have like been doing. I'm trying to think of this solution with like Gaussian elimination. Because in physics we learn to solve this exact same problem, but with another type of where is the Gaussian? Oh, I see. Probably between like all of the nodes. Total. We have the output between the nodes 1 and n rounded up to 2. Aha, I see that like you are from each of the nodes. You are saying that from I and BI is the resistance between A and BI is Ri. And then you're trying to solve for the resistance between 1 and n. And if you have this matrix of, but how would you construct this matrix where like you have okay, maybe do like a topological sort first. And then, but M can be really big here. I'm thinking of first like compressing these, because n is 220. That means that at most you will have 20 times 21 divided by 200 connections, 200 different connections. And then you can go from there and just try to combine the combined resistance. But this is solvable very differently on a very different. I don't see the implementation of God. I can solve it with a different approach. Okay, interesting. Central heating, what is this problem? It's again from Timos. Okay, let's see. Each of them is responsible for one or... there's a little problem. The university here only if all of the valves are open. So there's some technicians. Each of them is responsible for one or more valves. There may be several technicians responsible for one valve. Okay, when a technician gets the instruction to turn on heating, he goes around all of his valves and turns them. It means that if a valve was open, then he closes it. So he flips it. And if it was closed, he opens it. It is well known that every technician earns his money not in vain, so it's impossible to replace any technician. Okay. Oh, by any combination of other. So it means that all of these are linearly independent? Or what? It is very well known that everything earns his money not in vain, so it's impossible to replace any technician by any combination of other technicians. Your task is to determine who of the technician is to get an introduction to turn on the heating in order to heat all. To get an instruction to turn on heat. N technicians and N valves. Each of the technicians has some valves. The next N line contains a list. It means that the line I plus 1 contains the numbers of what ith technician is responsible for. Okay. I see. So you have these technicians, you each is responsible for some. So these different vectors. But then you want to flip these. This is a very interesting problem, because at first you won't think that it is what is this? So at first you don't think, well, they say it's impossible to replace. That means they're linearly independent. The combinations. So you have some vectors. So let's say this is the first technician. We have the second technician. Then the third technician. And who of the technician is to get an instruction to turn on the heating in order to heat all. Let's understand the solution here for this problem. Okay, technician 1 turns on this, technician 2, and output a list of technicians' numbers ordered in ascending order. If several layers are possible, output the shortest. If it's impossible to turn on heating, so what is this 1, 2, 3? Oh, the first technician turns 1 and 2, the second technician turns 2 and 3 and 4. I mean, it flips it, then this turns 2. Okay, so you want the sum of these. Because of the flips, we want actually an odd number of this sum. So you want to find a subset of technicians such that when they combine, when they combine, in each position you have an odd value. The minimum thing, and all of them are linearly independent. So if we solve the Gaussian, how will the system look? What will be the technicians here? What is the So you want the sum of I see. So you go through each technician, and you want this here to be this sum here to be equal to a number which is congruent to 1 modulo 2. On each of these columns, you want a number. Okay, so I see, I see. Well, yeah, this will give us our system of linear. Here, just like putting some other big odd number won't really work, but one will work, I think. So the solution to this problem is just creating a system of linear equation where for if this is the if this here is the vector for one technician, which light bulbs can turn on and off, then for each light bulb you want to have some constant times this, b times this, so each of these will be equal to 1. But now this modulo congruency is a bit interesting. And the what is this? So this is probably the solution to this problem, but I'm not going to try to implement it. I will try to see whether or not we can find a problem where it is pretty straightforward that we need to use Gauss-Jordan. I mean, not pretty straightforward, the problem which is designed to test out a snippet, a Gauss-Jordan snippet, because we have to test it out and we have to I think on eOlymp there are problems which I want just to test it out, to know that this snippet should work. And what is this? What is this? Like, there's no problem on eOlymp. I don't even remember what my password was here. I'm interested about this problem due to the if all of the resistors which are from one node to the other we can compress, and the resulting is actually 1 over this. I'm not sure about the precision though on this problem, and the fact that they only have one test case. How would you? Okay, I'm not sure about this. We may try to solve it. We may try to solve them. What is this block? The fear of Gaussian elimination. Actually, it's like due to the precision errors. It's so nasty, I think. It's just. I mean, it's good and keep going, people. I mean, it's a very interesting technique to know and to learn, but yeah, probably kind of useless in terms of like the probability that actually it's going to happen to know. Like the need to know it. But of course, it's cool. Now, one other thing I want just to quickly look is the orthogonal spaces. Now, I know that like using orthogonal spaces, we can. What is very interesting here is we can, using orthogonal spaces, we can solve for the solution of a system which is the closest to a possible to the optimal solution, but the optimal solution of course does not exist due to some like probably that the system is unsolvable, right? Now, is that used or so like this method? I'm not sure what was called the optimal squared method. The smallest square method. The smallest square method in competitive programming. I'm interested. Is that least squares problem? Least square problem? That was what is called? Of course, it's only linear, it's nothing too special. It's only papers, so I don't think that's even used anywhere in competitive programming. Although it could be cool to just like to say approximate the given line, you know, it might be cool addition to competitive programming nonetheless. Okay, so that is not used, so we can take a look at first at why it works before moving from our list. I mean, the least square method orthogonal space. I mean, we know why it works. I'm just interested in, is there some other interesting technique? Least squares regression. Some interesting technique or an algorithm which could be useful to us. Linear least squares, non-linear differences between linear and non-linear, uncertainty quantification, system testing, weighted relation to principal components. Yeah, principal component analysis. Tikhonov regulation, regularization. What is that? Regularization. We prefer. It's a constraint that L2 norm. Okay, this is just some kind of optimization. Gauss-Markov theorem. Okay, let's see what is this. Gauss-Markov theorem states that the ordinary least squares estimator has the lowest sampling variance within the class of linear unbiased estimators if the errors in the linear regression model are uncorrelated, have equal variances. I get it, but it's not important. I mean, it's probably way important. It's not important to me right now. What other thing we can use? We can see least absolute deviation. When I like hear about this least absolute deviation, it like already I'm thinking of some problems which I couldn't solve. Recursive reduction of dimensionality using linear programming. And another thing we should learn about is parametric searches. I'm interested about this technique, even though it's like very, very, very rare. Maybe it's something like, let's put some notes in what we should learn about learning. Let's put some notes in. Okay, let's, how do I, okay, just, I think you can see that. Okay, can you see that? No, it's too little. Okay, parametric search. That's one thing I wanna touch on maybe someday. Least deviation properties. Okay, probably this is way out of what I want. Orthogonal obligation. Okay, let's go back to Gauss, and because Gauss is our friend, we want to find a problem or try to solve one of these. The central heating problem. The central heating problem, because the congruency, it's not really, you know, I'm not feeling writing it. And then XOR maximization, even XOR maximizing. Let's see, what is this problem? Given set of integers, we define a function x on s as follows. That x on s is the XOR of the set. Given a set of n integers, compute the maximum of the x function over all subsets. Wait, what? Compute the maximum of the x function over all the subsets of the given starting set. So we want to pick. Again, this is the same problem. Again, we want to pick a subset of this such that the idea is the XOR is maximized. So maybe we try to. Okay, the subset is pretty big, but because this goes 10 to the 18, we only have 16 columns to work with, and due to the fact that 64 columns to work with, 60 columns to work with, and for each column, wait, is it 60? I see. The other problem was about. Okay, let's do some doodling again. Okay, so we have some XORs. Again, I'm going to produce them in vectors. I mean, we have some. These are integers. Let's say, like all of these integers, I want the maximum XOR. So this means from like any subset, I want to pick the subset which has the maximum. So this means that for each bit, I want the sum of this to be what are we supposed to print? We're supposed to print the maximum, only the maximum. The maximum will be given to us if and only we can compute the maximum if we know for each bit in the solution, is it on or is it off, right? So for each bit in the solution, the sum of these has to be one congruent mod 2. Yes, okay. So we just do a Gauss elimination on the, but we can't do on the set of the integers, right? They're too much. They're, unless we use the bit sets. What I want to say is we want to do like we want to make the vectors linearly independent of each other, unless they use this. For solving SLEI, the system of linear equations. What is this? System of linear algebraic. Okay, it stands for algebraic equations. We can use the however in case the modulo is equal to 2. So in case this is the, so this is our, this is what we're talking about. The modulo is equal to 2. We can perform Gauss-Jordan elimination much more effectively using bitwise operation in C++ bits. What is the complexity of this? Since we use bit compressed, the implementation is not only shorter but also 32 times faster. Okay, so the complexity is n cubic on the simple, but what is this acceleration thing here? The previous implementation can be sped up by 2 times by dividing the algorithm in 2 phases, forward and reverse. Similar to the previous implementation, but the current row is only added to the row after it. Okay. As a result, we obtain a triangular matrix instead of diagonal. Okay, yes, that's the thing. And then we reverse that on the other way around, right? Then plug this value to find the reverse phase only takes n times m, which is okay, but this is still wait, on the case where on the forward case, if we have some vector which is size of m, probably they think m is the column space, the column width. sure what is M. Okay, not important what is M. Let's say it's M the columns. Then for each n, we have n times m. To copy this to the next line. But also this. Okay. And then the reverse phase is n times m. So the algorithm should be n times m, right? So here, what is the idea? For each row, so for each column, for each row, we swap the rows. And then we XOR it. Interesting. Interesting, but it still takes, well, it doesn't, the n is, well, it should be now linear in case we have, okay, for each row, now we have n rows, right? Columns is only 30 whatever, right? So we're actually doing 32 times n times 2. Actually times n. Yes, I see. And this apparently works for, now A, what is A? A is given like a vector of bit sets. Then it's given n and m. Columns are n, rows are n. And then the answer is in a bit set again. We may try this, but yeah, okay. Okay. I don't think we can find here problems with goals. I don't think. Yeah. No. Okay, we may solve these, but okay, now we know a bit more, and we know that this actually speeds up a lot using bit sets. Okay, so we finished this. About Euler tours, I wanted to see a bit more. Of course, it's not linear algebra or anything. But maybe we should do some snippets first. Maybe we should do some snippets. Or we could go through some of my let's Google, let's see if Codeforces has anything on algebra Codeforces. Let's see on codeforces.com. Let's since it concerns linear, there need stuff going on in the background. Yes. Okay, the whole technique can be divided. Wait. Okay, now the problems that can be solved using this technique are actually not much hard to identify. The most common scenario involves you're given an array of numbers, and then the problem asks for an answer by considering all of the XOR sums of the numbers in all possible subsets of the array. So yeah, this is actually the whole technique we're talking about. This technique can also be used in some online query problems. The problem can provide queries of first type instructing you to insert numbers in the array without removal. I don't know how to solve with deletion of elements, okay? And in between those queries, asking for answers in separate queries of the second type. The whole technique can be divided into two main parts. Some problems can even be solved by using only the first part. First, represent each number in its binary form and consider it as a vector, what we did with this solution here. Each number is as a vector, where d is the maximum possible number of bits, yes. Then XOR of sum of the numbers is equivalent to addition of the corresponding vectors in the vector space. Yes, but congruently to in this binary vector space. I mean, it's not even addition; it's addition, but congruent to module 2. Somehow related to the answer and to the second type of queries with the basis. Somehow relate the answer to the queries of the second type with basis of the vectors found in part 1. I see. But yeah, how to do that? That's the problem. Let me explain the idea in plain English. No, okay, we know the idea in plain English. I'm not sure. Vector space, just a collection of vectors. Okay, problem division 2C. Find the number of non-empty subsets modulo this of a given set of size this with range elements to 70 such that the product of its elements is a square number. The product of its elements is a square number. This is the thing. We don't know what is the answer. You're just saying that the answer is a square number. Right? And I don't really have an idea of... Okay, maybe there are not a lot of square numbers that can be like find the number of non-empty subsets. But this is a number of non-empty subsets. You need to count them. Since the number of different possible masks were just 70 in the previous problem, we had been able to use dynamic programming for checking. Yeah, but okay, this is kind of interesting. I wanna learn more. Wait, what is the solution? Is dynamic programming or is the... Yeah, it's dynamic. No, I want to Gaussian to see. What if the constraint was much bigger? That is, we can use the part 2 of this technique. Okay, interesting. We need a couple of definitions now to move forward. All of the vectors mentioned in what follows include null vectors. I sincerely apologize for being so informal with these definitions. No, you don't have to apologize for this. Independent vectors, a set. Okay, we know what is independent vectors. Basis of a vector space, we know that too. For a set of independent, we can change any of these vectors by adding it to the linear count. Okay, that's true. The base vector is independent. Cannot possibly, and there cannot possibly be a larger number of independent vectors than bases in a set. Yes. So if you have like 70 columns and you do a Gaussian elimination, you get at most 70 independent vectors. No, regardless of the row count. Okay, this is what he wants to say. With just these few properties, we can experience some awesome solutions to a few hard problems. But first, we need to see how we can efficiently find the basis of a vector space of n vectors. Is quite awesome and works in. Wait, it's Gaussian, right? Like why? Oh, because it's in a binary space, then wait, you go into D and then what? But bit masks, insert a vector for D, mask is this. It's not basis of I. Basis of I. Base of I keeps the mask of the ith. It's not basis of I. If there's no basis vector with the ith bit set, then insert this. So you're okay. You're inserting each vector into this and then checking all of the basis vectors. I see. Mask is XOR to the basis vector. Yeah. What he's doing is Gaussian elimination on the fly. When inserting a vector, he's doing a Gaussian elimination through each of the basis vector already known, and then what he does is the ending vector. After all these Gaussian eliminations, is inserted into the base. But what if this ending vector is just a null vector? Probably like doesn't insert it. Okay, let's view some problems. Given a set with these elements, 2 to the 20 power, find the number of distinct integers that can be represented using XOR over the set of the given elements. I had a very similar problem on AdCoder the other day, but it was asking can you represent all of the numbers from 1 to 2 to the n power. In this way, we want to find the number of distinct integers that can be represented using XOR over the set of the given elements, which means that if we can do a if we can make a basis which is inherently linearly independent, has all the vectors linearly independent, we can count how many of these vectors are there in the basis, and then 2 to the power of that is actually our answer. I think this is the case of this problem. The solution is probably, yeah. Then the vector space, when we can find the basis in this time, any linear combination of the basis vectors will give this. So the answer is just 2 to the power of the size of the basis, which is really, really cool answer. Yeah. Okay, we got this problem down. Okay, let's take a look at this problem. We have a graph of 2 to the power of k nodes numbered from 0 to 2 to the k minus 1. Okay, where k is 30. Wait, oh, this is a large graph. Also, we're given integers, okay, within the range of this. In the graph, 2 vertices u and v are connected with an edge if and only if. Oh, the XOR of u and v is equal x. Okay, this is also this problem I have seen before. Find the number of connected components in the graph. Okay, so I have already seen this somewhere, where the XOR of u and v is xi. They're connected. Wait. For some I. So it doesn't matter for all i's, right? So what will be our basis here? We want to find the connected components, and all of these connected components have to be in some base. As I think so, right? Do they? Is xi. So xi for some I. Link to the source. The source of this problem is. What is the source? 2 special cases of Gaussian. Okay. I'm not sure what is here, UX or V. XI XOR V is here, but that doesn't. Put some good music on if you don't have, because there's always some good music. I'm not sure about this problem, we'll skip it for now. Given a set of these elements, of like n elements, find the number of distinct integers. No, this is the phi. What is the maximum possible XOR of elements of some set of S? This is the problem we actually encountered before. And what is the solution of this? I want to know. This problem we need to slightly also alter the definition. Find, instead of F being the first position with the set bit, let it be the last position with the set bit. Now to get the maximum, we need to initialize our answer to 0, and we start iterating through the basis vectors, starting with the one that has the highest value of f. So we start with the one which has the, because we need the maximum possible XOR, we start with the one that has the most, it's most significant, right? Suppose we're at the base vector b and we find that the answer doesn't have the b bit set. then we add b to the answer. This greedy solution works because it's most significant bit at the moment, and we must set it. Doesn't matter if the other following bits. Oh, this is incredible. Yes, okay. So we grab this vector, which has the most significant bit, we put it to the answer, right? And then we go to the next vector, which has a little bit most significant bit, and then we XOR it with the answer, and then we do that all the time. So we insert all of the vectors in A, and then we go through the most significant bit. If it's not in the base, we just continue. If the answer has already that bit, we already want to continue because we don't want to put any vector there. And if not, we want to XOR it. If there's like if there's no vector there, okay, I see. I see a very, very neat solution. I love this function. Actually, this seems to be a good function to have. So we learned actually a lot of things about the Gaussian elimination and XORs, which I'm surprised that like XORs have this property to be in this binary vector space. We have an empty set of S. Okay, this is much more like a complex problem here. We have an empty set S, and we're to do 1 million queries on it. Let X denote the set of all possible XOR sums. There are two types of queries. Insert an element to the set. Given k, print the kth highest number from X. This is guaranteed that. So a set of all possible XOR sums. Okay, now this could be using this technique here of the basis vectors, but actually what we can do is instead of just looking for the biggest XOR, we want to find the kth smallest, the kth highest, right? What we do is we want maybe to some kind of binary search. Try to okay, 10 to the 9, what is 10 to the 9 is, okay, 10 to the 9 is log 2 of 10 to the 9 is 30. 30 times is 30 million with binary searching. But no, we're gonna have even an upper bound binary searching, but binary searching has to check all of the basis vectors. The basis vectors are at most 30. So no, 600 million, that's too much. 600 million is too much. Maybe we can check it somehow else, of like using binary searching. X is highest number, or we can go from the top and to bottom, and then we know that if we use this bit, we at most can gain some number of. So for each bit, we can calculate how many numbers we gain by using this. No, that won't work. I see. So it has to be some kind of binary search. Let's see the solution. I see it doesn't use binary search. Okay, a bit like the previous one for query 2. Again, we'll iterate through the basis vectors according to the decreasing order of f values. Okay, that's is the one with the highest f value. Suppose BH is the one with the highest f value. Initially, we know there are 2 to the base size elements in X. Yes. So if K is this, we set the bth element to the answer to 0. Otherwise we set it to 1. This is very clever, very clever. We know that this is the case, and then we just compare to K. Well, okay, very clever, very clever. I'll try to solve these two problems on my own again, but just to refresh the understanding of these techniques. Beautiful techniques. Who wrote this blog is actually done an amazing job of capturing this technique. Dr. Schwat. Big shout out to Dr. Schwat. Is Tourist streaming? No, Tourist is going to stream tomorrow. I thought Tourist streams now. Okay. Let's see. Where were we? I like the problems. I like the problems because the statements are so short. This is what I like. I want a short statement, but it has like a lot of theory behind it. It has this linear algebra theory, which extends upon beyond every boundary. Okay, let's say this is division 2f. You're given an array. You have to answer 2 queries. In each query will be given 2 integers, L and X. Find the number of subsequences of the first L elements of the array, such that their bitwise OR sum is X. Their bitwise OR sum is X, and then we need to count the subsequences of the first L elements. Let me think about this one. The first L elements of this array. So do you have to answer the queries online? Because if you don't have to answer the queries online, we can probably sort the queries. Okay, what such that their bitwise OR is X. But the number, how do you count the number here? So it's above X. So how above X? How many numbers can you create from the basis of these L vectors above X? Can we just sort the queries and do this what we did in the previous problem? Is that the solution? Answer the queries online. Iterate through the prefix of the array for each prefix. Remember the basis vectors of that prefix. Okay, I see. Just remembering the basis vectors of that prefix. Okay, that won't be much because we only have n times n prefixes and times 30 basis vectors. Actually 20 basis vectors to the 1 power. 20 basis vectors. Okay, see, iterate to answer each query, actually representable or not, with slight modification. We don't need to add X, just check if it's representable, but just that's like iterating over iterating over this and just yeah, okay, interesting. If it passes all of this, then true. If just here, if it doesn't exist a base that we can do for this I. If this I is an X, and there's no base that can create them, that can create this ith vector, the ith component, then return false. Pretty clever, pretty clever, pretty clever. If you know like linear algebra, this is just mind-boggling, really, due to the fact that it's so elegantly represented. Although sorting queries in this problem will give you the advantage of not remembering all of the bases for each of these prefixes. Well, you can just create them. I wonder if this problem is it possible to be solved using segment trees? Like, is it possible that like you can merge two bases on two ranges using segment tree and then check? Ooh, this problem is gonna be insane. Wait. So imagine this, having a range from L to R, and then trying like on that range querying how many of these can be created using the bitwise this, and then just having a segment tree on top of this. A segment tree on top of the basis. A so-called augmented, I call it augmented segment tree. So this is pretty interesting, like having a segment tree on top of these bases. So like, yeah, I'll have to actually learn. Okay, what should we learn about? No, here I will just copy this, and I will say, no, wait, what? I want to copy this. How can I copy it? Okay, interesting problems to implement. Given an array in Q queries, each query consists of L and R and X. Find how many subsets from L to R can be represented. How many subsets from L to R have X or sum equal to X modulo equal. Find many subsets mod 10 to the 9 plus 7. Yeah, this. So given an array and Q queries, for each query you're given L and R and X. How many subsets from L to R to take? With segment tree and this whole technique. You have to find the maximum number of segments this array can be partitioned into such that each element is contained in exactly one segment. Each element is contained in exactly one segment. What does that mean? Each element. Okay, exactly one. Oh, I was reading it wrong. Each segment contains at least one element. Okay, I thought some other things. In distinctive segments. There doesn't exist a non-empty subset of segments such that the bitwise XOR of the numbers from them is equal to 0. what is a coding overload? Seriously? Are you? So why is OBS? Why is OBS doing this to me? Now probably it's fine, right? This is insane. Is it fine now? No, it's not fine. We have a problem on the OBS. Okay, now I think it's fine. I think it's fine. Okay, so where were we? You're given an array. You have to find the maximum number of segments that can be partitioned. So the maximum number of segments such that there doesn't exist a non-empty subsegment of elements bitwise or the numbers from them is equal to 0. Okay, this is a bit hard problem. You want these segments to be linearly independent. The XOR sums of these segments to be linearly independent. What does that mean? Why do we want that? We want it if it's linearly independent when the XOR sums are written like that. Say here as well we have. So this is the XOR sum of one segment. Then you have another XOR sum. Now we want all of the other sums to be linearly independent. That means that the Gaussian elimination of this matrix to be equal to have like to have as much segments as possible, right? While all of these the rank to be So while this is a base, so they're all linearly independent. We want the maximum number of segments such that they're all linearly independent. And they all have to be partitioned in a way that but how you partition this? You partition it by segmentation, not by just putting subsets on this. So okay, let me just think of this problem. So you have some segments. I mean, what is this? The array is this. Then you have to partition it such that the vectors when you partition the array are the maximum and they're all linearly independent. The most of these segments you will have is 30. That's the most number of segments you can have due to the fact that you have at most 2 to the 30 power on each of the digits. Actually 2 to the 28, so 28, but let's say 30. This is the number of the segments the number of segments you can have. Now how do you check if it's independent? How do you check for the most? You could have for each prefix, you could calculate XOR sum. And then you want, I don't know, I probably know. If I try, I may be able to solve it, but I don't know. I'm just not gonna waste time right now. Yeah, this is what I said, 31, the maximum of this. Probably some DP or something, what? Let PI be the XOR of the XOR sums of the I segments. Wait, let PI be the XOR of the XOR sums of the first I segment, and observe for every possible XOR of the numbers from some non-empty subset of these segments can also be obtained by XORing the sum of the... Okay, we know that. And vice versa. Which means that the XOR sums of the segments set of prefix XOR of the segment produce the exact same value as set of... So if the XOR sums of these segments has to be independent, then so does the prefix XOR. Wait, what? Really? Can you always partition it that way? Let Pi be the XOR of the XOR sums of the first I segment. So this segment, and some I segments. So then observe that every possible XOR of the numbers from some non-empty subset of these segments can also be obtained by XORing some subset from the set. Okay. And vice versa, which means that the set of XOR sums of the segments and the set of the prefix XORs of these segments produce the same exact set of values. So if the XOR sums of these segments has to be independent, so that the prefix XOR of these segments has to be independent as the sum of n prefix XORs in the array. Of all of these prefix XORs. Oh, I see. If you have like some prefix, then I see. The linear independent and independency of the prefixes. It means that the dimensionality of the prefixes. Yeah, it's pretty interesting. Nonetheless, some coder using this technique. What is the name of? I think some people Gaussian illumination module tour, but bitwise Gaussian illumination is a similar idea. Yeah, of course it's Gaussian illumination, but this thing here, this function of just okay, what is the best function just to have this function here, the insert vector function into this mask. It's just so cool. Let's create some like snippet for this function. Let's create some snippet for this function. Bitwise Gauss. Let's create some snippet for this function. I always like my snippets and structs. Okay, and we don't really care. This is constant. This is static constant. Here. If it's not added to the mask, return. This is insertion of this basis. What else we need here? We need I'm not actually sure I just think that like it would be better just to make it a vector thing. Wait, what? Just 31. Why? Why? What's the problem? Error type, error type. This is stupid. Oh, okay, you can't. Oh, we have to resize it here? No, we don't have to resize it if we know the. Be sure you can make this, but okay. Whatever. Bitwise Gauss basis resize. Okay, this gives our gives basis, and then what else? We can, of course, count. We can. I won't put count. Yeah, okay, it's enough. I think it's enough. Just to have this. Yeah, interesting. Is there some for these here problems? Is there some source we can solve these? Problems 1 and 2. All these problems can be modeled using. Oh, actually, this problem has been in Codeforces Run before. Interesting, and they give that much memory for it. And it's actually rated 2400. How is this problem rated 2400? That was with the first L of these. Yeah, well, if you don't know the technique, then it's 2400. Bitwise XOR is X. Yeah. What was the other problem? See, let's just check. What was the other problem here? Square subsets, yes. Now this problem is, okay, this 2000. I think Wait, for this problem, we didn't read the solution, right? Or did we? No, we didn't. This was this problem. Oh, we did, okay, we did, yeah. He had, this DP solution. Square of some. But he didn't say what is the solution to C. Okay. Let me take a look at the tutorial. Probably just getting the the tutorial is actually using this DP, but what is the DP? The DP is J XOR mask. Okay, not that important. I'll take a look at the problem later. Okay, interesting technique nonetheless. Very interesting technique. Can I upvote this block? I mean, it's nothing new, it's just linear algebra, but I love that actually this. Oh, you should enter into the system before. Okay, okie dokie, don't. Let me read some of the comments. What does Gupta has to say? Yeah. When you know linear algebra, it's just magic. I really like this orthogonal like minimization, but no one has actually used this. Bitwise OR of one or more integer between A and B. How many distinct numbers can be generated by bitwise OR of one or more integers? I see. be. See, just shifting the bits here, and that will work. Just shifting on the right here and on the problem A from Grand Conf. There are two persons, 0 on the variable x whose initial value is 0. The two persons now play a game. The game is played in n rounds. The following should be done in the ith round. The person Si does one of the following. Replace x with xx or ai. Okay, or do nothing. Person 0 aims to have x 0 at the end of the game. Person 0 is not x 0. Determine whether x becomes 0 when two persons play optimally. Probably this is meant like with some kind of dynamic programming here. It's not actually meant for this technique, but I wonder now if it can be solved. X is 0 at the end while person 1 aims to have x non-zero. If it's 0, it means the chosen vectors prior have been actually doesn't mean anything. Actually means that you have some, like, if it's 0, all of these are congruent with 0 modulo 2. The sum of all of these vectors that you have chosen is actually 0 congruent modulo 2. And then you probably want to, well, I don't know what you want. Well, if the basis vectors they have linearly independent. Oh, you just oh, I see. You go through all of the vectors, and then you do linearly independent vectors, and two persons play the game. The following should be done on the ith round. Person Si. Si. What is Si? Oh, Si is given. Okay, what person plays on which round? Okay, so you want the when this person here, when Si is actually person 1, you want to choose when person is 1, you want to choose you want to see if there is, what is the basis vectors for person 1, and what is the basis vectors for person 0, and then somehow see if these vector spaces annihilate each other. Alright, interesting problem. Yeah, how is subtracting synonymous from or? This is actually Gauss. Okay, interesting block, definitely worth 2 years ago. What about here? Is there something binary? We should do more. We shall do more of these. Second thread has on persistent data structures. I want to know. Multi-dimensional range queries. I have yet to solve one problem with like 2D segment trees. Dynamic connectivity problem. This is very good. Non-trivial DP tricks. Minimizations, theoretical grounds. Knapsack. Voronoi. Efficient. Oh, we shall. The next stream is going to be about solving some easy geometry problems, and in fact, we are going to solve. Actually, we're going to solve maybe some problems and try to find some good algorithms for some good snippets that we can like easily implement. I want to try to find snippets for it, which I can easily implement for in ACM problems, so I don't have to think about this. I just know the algorithm, just implement it, and because time is actually very precious. Geometry polygon algorithms. So yeah, convex hull algorithm. That is definitely for the next stream. Convex hull algorithm is actually for those who don't know, is an algorithm which, if you have some endpoints, it wants to draw a convex shape around all of these points, the minimum area convex shape around all of these points. Very interesting. There are a couple of different algorithms. So apparently OBS just reconnected it. Should be fine right now, right? Yeah, okay, it's fine. Okay, what other things we have in linear algebra? We have linear bases, okay, XOR bases extended to integers modulo composite number and beyond. Two special cases of Gaussian. This is the older one. XOR basis extended. Okay, this is a way, I think, way out of the scope of this video. And there, someone wrote a pseudocode for this algorithm. Okay, extended Euclides. Okay, this is way too much. No, this is no. But it's interesting to see. It's interesting that there is an extension to this. Although, yeah, problems with like, we can extend these problems on like segment trees and other data structures as well. Okay, yeah. What else? What else do we have here? Polynomial. So this is the actually the new cataloging on code forces. So this is the top of the blocks here. generating functions. Prefix sample. Yeah, FFT probably. We're not gonna touch on that. I mean, I solved some problems with FFT, but like this is too it needs too much optimizations. It's just bitwise convolutions, matrix exponentiation, Lagrange interval, no. Two set, randomized algorithms, non-exact. Okay, what is this Blogevoosh from Radewoosh? So like, I want to know what. I just want to know what is this. N words, every of length exactly 5 characters. Each character can be lowercase and uppercase digit. Basically, it can be any ASCII character. A task is to find all pairs of indices of words that are really different. Two words are really different if they differ at all 5 corresponding positions. So, for example, words really different or not due to what? Due to X. Okay. So 500,000 pairs. Probably it's just like some like this Borel paradox where like it's just random and lock-in. Yeah. It's yeah. It's just probability that. Let's see. I see. Square root decomposition. Yeah, we kind of need a snippet for that as well, because writing is just tries and suffix trees. I don't think anyone is gonna give tries, even though I tried to solve a problem with tries. Amazing. Sweeping lines. C++ trick sketching C. Okay, yeah, this is problem setting. Interesting. Why Cold Forces doesn't have a scroll bar? Are you insane? Okay. Interesting. So, okay, we touched on Gaussian elimination. On modulo 2 on the binary basis. So, yeah. Now let's return with this knowledge. Let's return just to take a look at these problems here. What was said about this technician problem? We said that already. This impossibility here. I think it refers to linearly independent basis vectors, and then this was just to determine who of the technicians is to get an instruction. Wait, if you do linearly independent basis vectors here, you're gonna get 1, 2, and 3. or not, right? Possibly not right. But let me write this vectors here. 1, 2, 1. Let me write them. Just I want to see what happens. 1, 1, 0, 0. 0, 1, 1, 1. 0, 1, 0, 0, and 0, 0, 0, 1. And you say that if we plug in this, this, and this, we get that the sum is of these vectors is 1, 1, 1, 1. Okay, now because these vectors can be very large, n can be very large, yeah, and cubic with Gauss. Yeah, so if we make a Gauss on this layer and this layer here, 1, 1, 0, 0 is going to remain, then 0, 1, 1, 1 is going to remain. The Gauss of these two layers is 0, 0, 1, 1. Then the 0, 0, 1. Then all of these are linearly independent. Am I right? Yeah. But why is this the case? Then we have to pull this, then we pull this and this, then we pull this and this. Wait, this and this will be 0 here. This and this will be 0. Okay, I'm just too tired. I don't know. Yeah, okay. Also, this can be solved without any of this stuff. I'm wondering if discussions mentioned that this can be solved without. Weak test. Author? This is the same author? No, this is Alexander Kleplinin. This here is Mengele. Okay, this is cool. Okay, I'll maybe take a look at these problems later. Okay, what else should we manage here? Well, no, I don't think today we're going to do anything about Euler tours. We have been live for 2 hours right now. Maybe we want to chill out something. Maybe want to chill out Euler tours. Let me take a look at this library here. I had like a library. I mean, it's not mine. I just somewhere was like not sure how was it called. Was that like that? Easy B? Oh, what libraries are used? No, not libraries. There was a guy who made competitive programming snippets, and a lot of them. Snippets, easy. And like I need to create a library of snippets as well. It's that color library. Does that color library has anything on Gaussian elimination? Math. What does math has? Convolutional. We don't want that. Chinese remainder theorem, floor sum. Floor sum, what is this? Okay, but this doesn't help me at all. Unless there could be that the library has more to offer than this is shown. I've never tried this in 128. Template functions. It's good to everything to be templated, but in ACMs you don't really have time. Here max flow. Change edge. Okay, max flow. We already have these snippets. CP is snippets. CP snippets. Clip, something like that. I have no idea. Let me take a look at on the second monitor on searches. Not sure why I can't find it. I don't have history, maybe bookmarks. Bookmarks manager. Oh, I find it. I found it. Yeah, this here, this thing. Okay. persistent symmetry. I want to see this. Externalization. Gauss. Yeah. So there are already nice functions implemented. But there's actually a matrix inverse with the Gaussian method. Let me see, what is this? Gauss-Jordan with full pivoting, solving, inverting, computing determinants. Yes, okay. Okay, this is one of the matrices. The second, what is the solve? Using this is the determinant. Oh, probably inside the algorithm itself, it just solves the Gauss. It inverts it. It prints out the determinant and the solution. Wait, this is the inverse in A. Why? Wait, why is the inverse in A? The solution in B. Okay, whatever. But yeah, okay, we have, what is this minimum assignment? This is actually like insane library here of just so many things. So many things. I just only want to see and persistent segmentary. Whoa, this is a short code for persistent segmentary. Whoa, you have to be kidding me. Wait, 3 of 5 plus 1 is update. Oh, I see. Okay, update returns some. What it does return? Wait, is it the whole tree copy or what? No, it's not, right? Okay. String hashing. That would be insane. Okay, these are probably algorithms and data structures that he wrote or he uses, and then these are some of external data, external resources. What does it have on like other matrix things? What does it have? Yeah, this is very usual, nothing special. Matrix tree. What is matrix tree? Submatrix wavelet. Matrix, never heard of this. You have no idea. It doesn't say. Oh, it says description variable message data structure for a list of integers in this range that admits the following queries in off-bit time: a rank a and k, x of I is a. Interesting. Okay, test matrix, max 0 submatrix, formatting number, like to have like this library in a book, I think it would be like this big. Maximum clicks, of course. Rotation sets. Probably you can see it, right? Max. Independence. Okay. Okay. Yeah, nice. So I have to, this is bookmarked. I have maybe to just put it here, just for like, okay. So this is going to be pretty much it for today. We took a look at a very interesting technique of the Gauss-Jordan elimination in the binary base. I just want to see what this algorithm here, what does it use? It just uses, is done with heuristic choosing maximum value in the current column due to the division. The division becomes has less errors. I see. Also, do CP program now have a GitHub or something? Do they have already these snippets here? Say linear algebra. So let's say determinant of Gauss, and then yeah, you have the snippet. Yeah, definitely we have to just get these snippets down. But yeah, let's create this as a bitwise Gauss snippet. Create snippet. CPP, enter snippet name. It's very interesting that this works online. Yeah, okay. Okay, now we'll know one more type of problem, which is not that common, but still it will be very, very useful to us. And yeah, that's pretty much it for today. We are going to resume the next stream. I don't know in how many days it's going to be, but we're going to try to solve some geometry problems in the next stream, because I really want to solve some geometry problems. And yeah, we had a nice time with the Gauss. Always linear algebra, always fun. So learn, stay creative, check out the channel, and yeah, always strive to learn new techniques, new tricks, solve new problems. Why not? One day you'll just be happy that you know these things. So yeah, peace out.